welcome to the presentation. My name is Tran. This is my colleague Ronert Obst, and we are both data scientists at Pivotal Labs. Today, we want to share our experiences and best practices with PySpark. Before we're just going to start with the presentation, it's noted that this talk is actually intended for people who have already some kind of experience with PySpark. So we assume that you have some kind of basic understanding of PySpark or Spark in general. So this is the plan for today. First of all, I will give a very short introduction into PySpark. Then Ronert is going to talk about data structure and giving some handy tips for the configuration and performances. Then I will speak about unit testing with PySpark, and then as well about data pipeline management. And then Ronert will give a small example about online learning with PySpark streaming. And then I will give an example of how you can put your models into production. So what is PySpark? Basically, PySpark is a Spark API for Python. So how does it actually work? Every time you start a PySpark application, so in a master node, it actually created a Python Spark context. And then through the Spark context, it actually used Py4j, which is also a Python module, to start a Java Spark context. And then the Java Spark context actually connects to the Spark workers on the remote worker machines. The remote work machines then actually starts Python subprocesses, and the communication happens through pipe. As you can see, compared to Scala or to Java, there will always additional time because you have to start the Python subprocess during the PySpark application. And also a very important note is in terms of the data, because data will be serialized in both the JVM and the Python subprocess, which this will also cost additional time. Another important point in terms of this architecture is that the Python memory isn't actually controlled by the JVM. So for example, if you probably have a very reasonable settings in Yarn or something like this, you still might get some kind of out-of-memory error. But this is a topic that Ronert will take more.
Yeah, let's review some of the data structures in PySpark. We have resilient distributed data sets, which everything else is built on. These are a fault-tolerant collection of items, and they support two types of operations: transformations and actions. Transformations, they are always lazy, so they're not. So when you execute a transformation, these are not evaluated immediately. Only when you perform an action on these transformations. And another important note is that RDDs are immutable. The other important data structure is our data frames. Data frames are collections of rows with a schema, and for the most part, these are kept within the JVM. So they have a very large performance advantage over the native, over using RDDs with PySpark. The notable exception here are if you're using Python UDFs. And so you should always use native functions whenever possible. And what data frames do, if you run these native operations on them, they take your Python calls and compile them down to native Java bytecode. And because these data frames, they have metadata about the types contained in them and so on, you're able to run many more optimizations on them, hence the performance improvement. And one last tip is you should always create data frames with a Hive context and not a default SQL context, because you get many more UDFs, you get window functions and so on, so there's quite a lot of advantages there. And you don't even need a Hive installed to use the Hive context. This is a benchmark of using Python data frames as opposed to Spark data frames as opposed to RDDs. What you can see in this benchmark is that they have the Python Spark data frames. They have exactly the same performance in this group by reduce operation as the native Scala code, and this is because both use the compile down to Java bytecode. Whereas if you're using RDDs, there's a lot of performance degradation for using Python as opposed to the native Scala API. And this happens because there's serialization happens in two places, as that noted. When the Python process writes something to an RDD, it is serialized as pickle, and when it reads it again, it's deserialized as pickle again. So there's this serialization happens twice there. And finally, there is a new data structure in PySpark that came in 1.6. This is a data set. This is not available in PySpark yet, only in Java and Scala. And it's statically typed, so limiting the space further of what can be expressed enables even more optimization, similar to what is available in a database. So the query optimizer is able to do much more with this. This is actually a data structure which is taken from the Apache Flink project. And in Spark 2.0, these two data structures, they will be unified, like they are in Apache Flink now. It's not clear yet how these will be handled in PySpark, because Python is, of course, not a statically typed language, so maybe a bit awkward to handle, but it will come with a lot of performance advantages. Configuring Spark is actually the most difficult part in practice, what we have encountered. So, first of all, let's have a look at configuration precedents. There are three places in PySpark where you can set your configuration. First of all, programmatically within your actual script using the sparkconf command. Then you can pass configuration options to the command line. And finally, you can set all the options also in the Spark configuration files. And they have a certain order of precedence. So what you set programmatically always overrides what you set in the command line and what you set in your configuration files, such that these take precedence. And what you set in the command line takes precedence over what you set in your configuration files. Spark memory management used to be the most complicated part of running Spark. In Spark 1.5 and below, there used to be two separate memory managers for execution memory and storage memory. And this caused a lot of problems. Execution memory is where you compute shuffles, join, and so on. So these sort of things spill into execution memory, whereas storage memory is used for caching and distributing internal data sources across clusters. And then there's user memory. User memory you can use to store your own data structures. You can basically do whatever you want in the user memory. Now, the big change that came in Spark 1.6 is that the boundary between storage and execution memory became dynamic. So Spark handles this boundary. It can shift this boundary. And this is a really, really big advantage because in Spark 1.5, it used to be the case that if you, for example, set your storage memory fraction to 0.5, but your execution memory was temporarily larger, it started spilling to disk instead of taking the empty storage memory, right? So for every single Spark script you ran, you actually had to fiddle around with this storage memory fraction. And this is gone in Spark 1.6, so configuration became much, much easier. But let's jump to a worked example, because in the docs, it tells you what each option in PySpark means, each configuration option. But when I read this documentation, I had absolutely no idea what I should actually set the values to. We have to start with yarn config. We have an example here with 6 nodes. Each have 16 cores and 64 gigabytes of RAM each. And you have to leave some resources for the OS and the Hadoop processes. So you'd approximately set your node manager resources to about 61 gigabytes in this example. And you also have to leave 1 core for the OS here. So you use about 15 cores here. What you also have to do is to get the most out of your cluster and avoid network and I/O CPU weight. You should overcommit your resources by about a factor of 1.5. So in our example here, we're using 4 executors with 6 executor cores each on 6 nodes. And that leaves you with an executor memory of 11,600 megabytes for each node. And what is also important to note is that the Python memory is managed outside of the JVM process, so it comes on top of this. By default, each Python process is given 512 megabytes of RAM. Now, because we have 24 executors, we have 24 of these processes, and this is something we have to take in mind. And if you get Python out-of-memory errors, one thing you can do is you can reduce concurrency. So you can go down to, for example, 4 executors per node. And why would you want to do this? So, for example, what we have done in the past, we've used PySpark, for example, to drive cross-validation from scikit-learn to parallelize it over a cluster, right? And if you're starting to fit models within PySpark, you definitely need more than 512 megabytes of RAM. So what happens is you start getting out-of-memory errors. And that's when you have to reduce this concurrency and start increasing your Spark Python worker memory. And this leaves you with less executor memory, but that's how you can avoid these out-of-memory errors. Some other useful settings we have found is that you can save substantial memory in PySpark by turning compression on. And if you run PySpark in a cluster, you should always enable speculative execution. Speculative execution means that if a worker is particularly slow or fails, Spark will automatically restart that task before the other worker returns or fails or returns an error or something. So this will speed up things a lot if you have one slow worker in your cluster that is slowly starting to degrade. Something we've really struggled with because we exclusively work with Python 3 is there are many issues using Python 3 in PySpark because in Python 3 there's a new security feature where you use hash randomization to provide protection against denial of service attacks. Now this means that in a cluster environment, Python 3 will fail on group by and reduce by key operations. And just exporting the Python hash seed on the main node will not resolve this issue. So if you want to use Python 3 in a cluster environment, you have to set this setting in your sparkdefaults.conf. Otherwise, things will go wrong. And if you want to tune performance, there are several things to keep in mind. One thing is you should always cache your RDDs you're going to reuse. So for example, if you take again an example of using cross-validation distributed among your cluster, you're going to use that RDD many times during your cross-validation, either with MLlib or scikit-learn. So what you want to do is cache that data before running cross-validation. Otherwise, your RDDs will keep being recomputed, and this is going to slow down things a lot. Another thing is you should avoid group by key whenever possible, because this requires all values for a single key to fit into memory. And this will actually not happen if you use a data frame group by key, because it uses this optimizer, like in a database. And one thing I don't think enough people know about yet is that you can actually distribute data by key now since Spark 1.6. This is a really important feature because what Spark used to do is randomly distribute data by a hash. And if you then ran a group by operation, it needed to do a shuffle and collect all the data of a particular group in one node, right? But if you have a use case, for example, if you want to fit one scikit-learn model per group, say you're a global company and you want to calculate one churn model per country with scikit-learn. So you want to basically do a group by and then map your scikit-learn model over this group data. then there would be a lot of shuffles on your cluster, and things would go out of memory or fail or something like that. And so what you can do now, since Spark 1.6, is you can actually, if you know ahead of time what key you're going to do this computation on, you can actually, when you read in a data frame or RDD, you can repartition it and then already group it by key when reading in the data, such that when you do this operation, there needs to be no shuffles. And that really speeds up things a lot. And then two things here. Always prefer tree reduce and tree aggregate over the standard reduce and aggregate functions, because these use much more intelligent binary tree algorithms to compute these aggregates by computing intermediate results. Whereas with the standard reduce function, one node could become a huge bottleneck. And finally, if you have lookup tables, you should always broadcast these, or small tables with frequently accessed values, because otherwise these keep having to be shuffled around the cluster. Now on to unit testing with PySpark.
So before starting with this, who of you have a computer science background? Well, it's not much, but okay. So let's start with a situation that some of you might know. So there's a PhD student with his professor. He probably doesn't have a computer science background because, right? So he says like he wrote a code. It's inelegant. It's messy. It's inefficient. And oh, can you guys read this? So he says like, well, I finished the computer program I needed for my research. It's not pretty, but it works. It's inelegant, messy, inefficient. And if you try to change anything about it, it will probably explode. And the professor says, well, it sounds like every academic I've met. Great, can I get my PhD now? So you know the situation, right? So I mean, most data scientists doesn't have a computer science background. So this is a situation which is probably fine in academia, but in reality, it can be a little difficult, because if you, for example, put your code into production, right, you have a lot of code, and spending time on debugging bugs is quite problematic, because if you ever wrote a code that is used in production, you will know this experience. So what is this solution to this? Well, at Pivot Labs, we have a core practice which is called TDD. So it stands for test-driven development. And what is actually TDD? Well, in the TDD, you actually start to write your test first. And then you write as little as code as possible to have the test pass. And then you just refactor your code. So this is actually TDD. Of course, so far, this has been a great benefits for our software engineers, so we are pretty famous for this kind of approach. But surely, the reality can, of course, be difficult for us, right? Because we're not software engineers. Most of us are data scientists. So in a software engineer, you probably might like program an app. And in this app, you have a button. And the button, for example, is red, right? So writing a unit test for a button that is red is much easier. But in a data science context, you get a problem, right? And you're trying to solve this problem with some different models, right? And at first, you don't know if this model is going to work. So there's a lot of R&D or uncertainty or stochastic component involved in this. And that's why what we actually do is we split it into two phases. So there is one phase which is called exploration phase, and the other phase is called the production phase. In the exploration phase, what we actually do is we use IPython notebook and all of these things to experiment with different models. We do cross-validation, something like this. But during this phase, we also get to know a lot of the models, right? And also the output, what you get. So for example, let's say there's a use case. There's a company. They want to rate the client, right? So a typical approach, which is like to use clustering method. For example, like k-means. So, and in k-means, what you do is you might need to transform your data. You rescale your data because k-means works better in this way. And then at the end of the day, you fit your data, you get the cluster centers, and then you just use your function to assign this to a label, right? Of course, using IPython notebook is of course not optimal. For example, you know that this rating works, and it works well, and then you want to put your code into production, right? Because it should be done automatically. And that's why in the next step, what we call is actually called production phase. So we're trying to put everything that we've done in the IPython notebook in a script. And here actually starts the TDD approach. So for this, in terms of PySpark, what we do for testing is we're using a single node Spark application. And if you're on a Mac OS, it's really easy to install it. So you just use brew to install the Spark apps. And then also what you can see is we just assign it to 1 GB memory and just 1 core. So it's a local system. And a very important point as well is when we write a test, we actually mock the data. So in a unit test, the test should be run pretty fast. So that's why we're not reading from a real database. This is actually how a test looks like. So relating to the clustering example again, usually you convert your data frame, right? Then you rescale your data, and then you assign it to clusters. And because we're mocking the data, we have some kind of understanding of the data and the algorithm. So actually, TDD forces you to think about how the algorithm works, right? Because most of the people just use a model, an algorithm from R or any package, and then they just fit it. So they never trying to understand what the meaning of this algorithm is and what it does actually. So at a TDD, you need to think about this. And then what you actually do afterwards, when you wrote the test is probably failing because there's no implementation, right? So you start to write your implementation. And basically, this is the minimum viable code that you can write to have the test pass. But still, of course, there's some points that you can do. Like, for example, K is 2, C is 1, and something like this. You can create global variables instead of the variables within the function. So you still can do some refactoring. I actually put a full example how you would implement the clustering example. So it's on my repo, so you can check it out later. Another important topic that I want to talk today shortly is about data pipeline management. Do you have a question? Is actually pipeline management. So as you might know, so in a model or something like this, there are a lot of different steps involved, right? So you're reading from a database, and then you're fitting your model, and then you're predicting. For example, in the clustering example, you might read from a database and use a SQL script. And in SQL, you also do some transformation. And then in a Python script, you train your model, you parallelize this model, right? And then you fit the model, and you do cross-validation. So doing all this step is actually sequential and depends, and there are some dependencies within this. And of course, if you just look at the clustering example, it's quite small. But if you add more use cases more and more when time goes by, it can become quite complex. So what we did actually in the past, we wrote our own pipeline script in Python. So here in this example, we actually chained SQL and Python together. One of the disadvantages in this approach is when you use Spark Smith and for example, have it run through a cron job, the files, the SQL files and the Python script have to be distributed in all the worker nodes. Just imagine you have 10 worker machines, right? You have to, for example, if you're not smart enough to just SSH into all of these machines and then upload it. Or, of course, you can also use like PSSH or PSCP to upload all the files. But this is quite a hassle because every time you change your code, you have to upload it again. And another important point is, of course, you have to write your custom loggers. And we spend a fair amount of writing our custom logging information. And if you're already dead with the logging module, it's quite powerful, but it's also quite time-consuming. That's why what we did is we switched to Luigi. Luigi is a pipeline module, which is developed by Spotify. It's 100% Python. It comes along with a web dashboard. You have parallel workers. You can pass parameters through it, and it has many templates for various tasks, like Spark as well. It is not as powerful as Airflow or something like this, but it actually serves our purposes. This is actually an example of how you would write a task for Spark. So you actually just import the Spark submit task. Here in this example, I'm referring to the clustering example again. So I'm actually defining some parameters like the number of k, which I just can pass in a cron job. And then I also added this to additional options. And this is actually the pretty cool thing. So you can just specify your dependencies in just one-liner. So in this case, the feature engineering task has to run first, and then the clustering task will run afterwards. This is actually what we also do. So we usually don't specify the configuration in Programmatic anymore, but we have a Luigi config file where we also specify settings for Spark as well. And with this, actually, the architecture changed. So in this kind of approach, you don't need to upload or distribute all your SQL and Python files anymore, but you just run it from the master node. So it's much more convenient. Of course, there are some caveats. You don't have a built-on job trigger, so we still have to use cron job. The documentation could be better. Logging is quite OK, but when you have multiple workers, they could cause much hassle. And if you have many tasks, there could be a problem with the parameters because you have to pass all of this as well.
Onto a new feature of Spark is online learning with PySpark. This is actually something I want to point out to you. It's not a concrete how-to. But lately, we've experimented with using Spark's stream processing and online learning capabilities of MLlib's stochastic gradient-based, descent-based methods to create real-time machine learning models, which can update themselves on new data in the stream as it arrives. And at the moment, only streaming linear regression and streaming k-means is implemented, but many more models are coming in the future. There are quite interesting use cases with this. For example, what you can do is, if you're running an A/B test, you can actually run multiple models within your Spark streaming context and evaluate this in real time. And for example, using a Bayesian bandit approach, try to optimize these models in real time and always only expose the optimal models to your user. Another use case would be performance monitoring. So for example, if performance suddenly starts to degrade in your models, you can send out an alert and so on. And a third use case would be if the data generating process changes, right? So you have the possibility that the model adapts to that change very, very quickly as data streams in, unlike in a batch environment where maybe you compute a new model every week or every day or something like this. In this sort of setting, you're able to adapt to changes extremely quickly. Under the hood, MLlib in its streaming algorithms uses for each RDD and map to make these computations. If you look at the source code, the implementation is actually quite straightforward. One downside with Spark streaming is that it operates on mini batches. That means it takes a chunk of data and then does a computation. So essentially, it's doing a batch operation, but only at certain fixed time steps. So it's not really a true streaming framework. That means in a distributed setting, you'll never get better latency than about 1 second. So it's not something you can use, for example, as a predictive API if you need a fast response. In that regard, Apache Flink is also a very promising project because it can evaluate these streams in real time, and it also has a very powerful similar capabilities to Spark. But the problem is that at the moment, there is no good and well-documented Python API for Flink. But this is also an interesting project to watch in regards to online learning. And finally, onto operationalization.
Can we still have 3 minutes? Okay.
Yeah,
Okay. Yeah.
go for 5 minutes or so. Yeah, 3 minutes.
3 minutes?
Yeah.
Or okay.
2, okay.
2. Okay. Well, I'll make it quite fast. Okay. So actually, at Pivotal Labs, we.
10 minutes. So I mean, you can.
Okay.
Have 5 and then questions.
Yeah. Basically, this is a very important topic actually. So at Pivotal Labs, we actually follow an API-first approach. So we try to put every model that we do in an API, and for doing so, we are using Flask. And Flask, who of you have ever heard of Flask? Okay, cool. So you know what Flask is, right? So Flask is a lightweighted web framework. And what we actually do here is we usually train our model in PySpark, and then we pickle it to like, for example, a database like Redis or an HDFS, like the file system HDFS. And then what we do is then we load the model. And afterwards, we write our own function to predict like the label in this case. This is also a very fairly example. So I usually I use post to post some data through JSON, and then from the JSON file, I actually create a PyData data frame, and then from there, I use the predict function with the model to return a label. In reality, the output of this Flask API is much more complicated, right? Because here in this example, you would just get the label. But for example, if you're in a prediction use case or something like this, you might get a dictionary of probabilities and some metadata along with this. So, but I think with this example, you probably get the idea. So, as I said, again, we actually use Flask to create the API. But of course, for deploying it, you cannot use Worksock or something like this, right? So for deploying, we're actually using Cloud Foundry. Have you ever heard of Cloud Foundry before? Okay. So, okay, 3 people. So it's not a lot. So Cloud Foundry is actually an open source project, and Pivotal is also one of the biggest committer. It is actually a platform as a service. If you ever have deployed an API before, it's quite a hassle, right? Because you have to take care of the load balancing, you have to take care of routing, or for example, if you also change of your code, right? You have to put it on the VM again and something like this. So there's a lot of things. And actually what this quote from one of our colleagues says is, here's my source code, run it on the cloud for me, I don't care how. So this is actually what Cloud Foundry is doing for you. Actually, we also have a trial version, so it's for 2 months. So check it out if you want to use it. And also, one of my colleagues in Houston, he presented CF last year on PyData. There are some examples with Python and CF. It's also worth checking this out. Okay, that's it. Time for questions.
Thank you very much. Are there any questions?
I have 2 questions. First one is like, at the beginning you mentioned this data structure. So you compare the Python RDD, PySpark RDD and also Scala RDD. Yeah. It's like much slower, right?
Yeah.
So,
yeah.
So what's the advantage to use the PySpark instead of Scala Spark?
Well, Python is a very we're at a Python conference, so we love using Python, and it's also an easier language to use. So many people in the PyData community, they come from have an academic background, so they don't have a computer science background, and are not be necessarily comfortable to use a statically typed programming language like Scala. And so they're used to Python from doing computations on a local machine, using pandas, using scikit-learn, and so on. Yeah. So this is something much easier for them than getting into something like Scala.
Yeah. Anyway, so the second question is like you said that you tried a very specific question, like avoid to use the reduce by k, yes. Right? So once you need to use this, because this is always the problem is I tried. So if you really need to use this reduce by k, I mean you have to reduce them. So what do you do? What's the typical strategy to avoid it after?
So actually not reduced by key, but grouped by key. So strategy to avoid it. It's a difficult question. I mean, there's just some operations where you have to.
Yeah.
That's why I gave the second tip. If you know you're going to group by a key ahead of time, and this key is going to fit on a node, when you read in the data, already partition it in such a way that it's partitioned by that key, such that no shuffle has to happen. This will really help performance a lot. But yeah, there's some operations where you can't avoid this. But if you actually, what you should avoid is doing a group by key and then a reduce. What you should run instead is this tree reduce function, because it will compute intermediate results on the various workers and not put everything in one node.
So we also have some use cases with group by key where we cannot avoid it, right? So it depends really on what you want to do.
Okay, thank you.
Thanks for your talk. I just had a quick question. When you did encounter memory issues, how did you debug them?
How do we debug them? I mean, sometimes the error messages, they are very, very non-informative. It's just what you do. You Google and look at Stack Overflow and try to figure things out. But I mean, there's no,
I mean, if you experience work with Spark for a couple of months now, it's much easier now to understand the problem, but it's kind of difficult. And especially also when you do unit testing as well. So a very handy tip is actually to turn off the logging from info to error, because then you don't get all these things like what is the partition in which working machine and something like this. So yeah, and also for PySpark, actually, unit testing can also be quite difficult because of the communication between Py4j. So you get the logging from Py4j, and then the error message which is sent through Py4j is quite useless.
And then there's also the web UI, which has gotten a lot better recently. You can actually see the query plan of your whatever you're executing, so you can monitor what's going wrong. Yes?
Is there any cases when you use the cache? Can you use a mic, please?
Yeah.
Is there any cases when you use the cache with just the memory, it tends to recompute everything?
No, I haven't encountered an example where I set it to memory only, because that causes a lot of problems. If you set it to memory only, and the cluster runs out of memory, it's expelled from memory. But if you set it to memory and disk, if the cluster runs out of memory, it's serialized to disk at least. So it hasn't, the RDD or data frame doesn't have to be recomputed from scratch. At least it can read it from disk. And I haven't encountered an example where setting it to memory only would be of advantage.
And so to get all the Python libraries required for machine learning, is it installed along with the cluster install, or we have to have a separate process to have all the Python libraries as part of the cluster?
What we do is we install Anaconda on every single cluster node, and then set the Python path to Anaconda. But Continuum has come out with actually a cluster management service where you can do this much more easily and push Conda environments to the cluster, but it's a paid-for service.
So basically what you can do, there are some free open source things like PSSH and PSCP, where you can also distribute your files on a different different working machines.
And is there a way to just have all the Python libraries only for specific number of worker nodes?
What do you mean?
I'm not sure I understand. You want to only
just to avoid the impact of the Python libraries on other applications.
You want to only install them on a couple of worker nodes?
Yeah, so if you want to configure a certain number of nodes for data science.
Then you just specify them in whatever you're using to push it to the environment. You just specify the hosts you would want to push these to, but there's no shortcut or something we've figured out.
Thank you.
Have you had any experience of using the sort of window functions on the data frames, like the SQL window functions? And are there any kind of similar traps when you're grouping by there? Or?
No, because at least we haven't encountered any, because first of all, it's able to use the optimizer. So instead of having to guess everything, it's able to actually produce a very smart execution plan. And usually, we haven't encountered any problems there yet. Yes, please.
Yes.
Apart from more documentation, what else would you... Oh, sorry. Apart from better documentation, what more are you hoping to see come out from Spark in the future?
One thing is maybe better, more comprehensive online learning libraries, more focus on generally the MLlib library, and also potentially that the Python API doesn't lag behind slightly as compared to the Scala API. At least that's my idea. Do you have any?
Yeah, I mean, it's just adding some points. So like the machine learning library, right? They're like binary classification is much better in Scala than in Python, and it's already implemented in Scala. You just don't see the function. Also in the documentation, there are some things hidden that you don't see because it's just not updated. So it might worthwhile to read the Apache Spark documentation, the raw version, not the use case, the examples that they give. So.
Okay, well, we have actually no more time, but maybe one more question.
One more question.
How do you generally store your data on disk for performance?
Parquet.
Parquet.
Yeah.
Actually, this is a slide we had to take out due to time. If you actually want to use Spark together with some SQL and Hadoop engines, because Spark SQL is not so advanced yet, sometimes you instead would want to use a SQL and Hadoop engine, such as, for example, a Hawk or Impala or something like this. And you can actually share data between these using Parquet, because Parquet contains the metadata around the schema and so on. So that's very good. It's also got really, really good performance as compared to the other file formats.
Have you tried awk?
Sorry?
But awk as well. It's similar. Awk files?
ORC.
ORC.
I personally haven't. We haven't tested ORC yet, but I assume But Parquet is a fairly default format for many applications running on top of Hadoop now. So you can interchange it with many other applications. I think we're out
done
of time.
Okay. Thank you very much.
Thanks.